think they don't understand. So let me ask a couple of probability questions, and you could tell me whether these are sort of appropriate for their level. So I don't know if you guys watch baseball or sports or anything of this sort. No. Anyway, the World Series has been going on, and this is a best of 7 series. So you have to win 4 out of 7 games to win and be really excited. So when the first game arrives, the analysts get on. They're really excited. They want to drum up, excitement for the game and tell you how important game 1 is going to be. And they look through their statistics, the data that they found in the past, and they tell you that the winner of game 1 of the series wins the series 65% of the time. And you're supposed to think, oh my God, 65%, that's incredible. And okay, so game 1 happens, somebody wins, they're still talking about game 1, it's amazing, 65%. Okay, game 2 comes, and guess what they say? The winner of game 2 wins the series 65% of the time. And you think, okay, seems pretty similar. Game 3 comes. 65% of the time, the winner of game 3 is the winner. Guess what about game 4? 65%. Game 5 comes along. What do you think the answer is? Actually, no. Game 5, the probability goes up. The reason is because in game 5, the fact that there is a game 5 comes already with an assumption about the state of the series. There's no way it's 4-0. That's out of the question, because otherwise it's over. So that assumption itself is already kind of a conditional probability question. So here's my question. So they say it's 65%. This is based on data from the past. Is this exactly the amount that we should expect, assuming that both teams are equally good? Each team is equally likely to win each game. What is the probability that Team A wins the series, given that they've won game 1? So what do you guys think? How would we think about that problem?
Well, they have to win 3 more games out of 6 more games.
Right. And it can be in any order. Right. So, of the 6 remaining games, they could either win 3 of those, they'd win the series. They could win 4 of them and they'd win the series. Or they could win 5, or they could win 6. So, how many ways are there for them to win 3? You don't have to give me the exact number, just a way that we could calculate it. What's that? 120. It's got to be like
A, B, 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 A, B, 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 A, A, B, B, A.
Right. Yeah, so the way this is calculated, am I allowed to write on here? Is that permitted? Okay. So,
How many different ways you can do it? So it's the number combination of 3 things. What, 6 factorial over 3 factorial, 3 factorial?
exactly, yeah, it's 6 choose 3,
20 ways?
which is 6 factorial over 6 minus 3 factorial times 3 factorial. I don't know if that's a visible table.
Yeah, the number of combinations, not the.
Exactly. So the order doesn't matter. Once you've won the 3 games, there's no sense in reordering the 3 games that you've won.
Right.
That doesn't matter. So that's why the 3 factorial is down here, because you're dividing by the number of ways to reorder the 3 winning games. But there's this many, I guess this is 20. So that's the number of ways of winning 3. So the number of ways of winning 4, we can do a similar calculation. 6 factorial over 6 minus 4 factorial, 2 factorial.
Could you move that chair so we can see?
Oh, I'm sorry. Yes.
I see if one of these works better. So maybe it's the more predictable as well.
Okay. Okay, thanks.
There's one on the table right
Okay, was this one working?
I guess.
Okay, I'll stick to this one. So this one I think will compute to 15.
So we're n factorial over n minus r factorial r factorial.
Good.
Um,
Once we compute this, and so we'll get 6 factorial over 5 factorial, that's 6. And the very last one, there's only one way to choose 6 elements from a list of 6. So, these are the number of ways that we will win the series if we're Team A. And so we'll add these up, so there's 35, 42 ways to win. How many ways are there to lose?
42.
What's that?
42.
Well, remember we're leading.
No, that won't be.
So we've won,
Because
we're Team A, we've
3.
won game 1.
We'd have to, so it'd be 22.
Right. So,
You take the 3 out.
exactly. So the 6 choose 3. If the opponent wins 3 games, they're not going to win the series because we've already won 1. Right. So this is gone. The number of ways to lose will be 15 plus 6 plus 1. So 22.
So 42.
So after all those calculations are said and done, we've got 42 ways to win, and we've got 22 ways to lose. So our win probability is going to be 42 divided by 42 plus 22. And I think this is actually roughly 65, or 0.65. So the 65% win chance appears to be about correct. That really is what should happen. Any questions about what we're doing here, about this stuff about combinations? Is this sort of the type of thing that you would want your students to be able to do for the competition? Yeah, okay. What's going to change when we start talking about the winner of game 2? Suppose we assume in advance that Team A won game 2, but nothing about game 1.
No, it's the same.
It's going to be exactly the same. There's no assumption about game 1 at all. So there's no conditional probability going on here. Game 2 is just the same.
Yeah.
So game 2 comes along, the announcers say the same thing, they want to make it sound super important, but it's not the same as game 1.
Exactly the same. Same for game 3.
Same for game 3, and the same for game 4.
Yeah.
Now, we know that by the time you get to game 7, if it gets to game 7, the winner of game 7 wins 100% of the time. So something changes towards the end. The difference is the fact that there is a game 7 comes automatically with an assumption about the current state of the series, that it's 3-3 in that case. So we sort of know what's going on there. But let's think about game 6. Okay, so I'm going to assume here Team A wins game 6.
That was the Red Sox.
So, what's up?
I said that was the Red Sox.
That was pretty awesome, right? I don't know if anybody's I grew up in Boston, so this is on my mind,
So that felt
which is
really
why I'm
good.
talking about it. If the Cardinals had won, I would never be discussing baseball right now.
I would.
I know, I'm sorry. They were a great team, and it was a fantastic series. So that walk is pretty amazing. So assuming Team A wins game 6, what implicit assumptions do we have, just based on our knowledge that there is a game 6?
Team B has won at least one game. There's 2
Yeah.
games.
In fact, yeah, so it's either, in fact, haven't they won at least 2 games?
Yeah.
Yeah.
So it's got to be 3-2 in favor of somebody. So there's 2 cases I have to think about here. Case 1 will be Team A leads 3-2. Given that Team A wins Game 6, what's their win probability in the series? 100%, yeah. So in this case, we have a win probability. What if Team B leads 3-2?
The ties have a 50% chance.
Exactly. So our win probability in this case is 0.5. So both of those outcomes are equally likely because case 1 and case 2 are equally likely because we're assuming that the two teams are perfectly evenly matched, maybe like this year's World Series. So each of these are going to happen roughly the same number of times. So on average, the winner of Game 6 is going to win 75% of the time. Game 6 winner wins 75%. So all this hype about how likely it is that you're going to win the series, and if you win Game 6 or if you win Game 4, all of it just seems to be a little overrated. I think.
It's Game 6.
Yeah, so Game 6 is getting more important. Game 5, we can do a similar analysis. We'd have to think about 3 cases there. The 3-1 case, the 2-2 case, and the 1-3 case. And we get some answer between 65 and 75%. And of course, once you get to Game 7, you win the series. This is kind of an exercise in conditional probability. The first 4 games are not a conditional probability question at all. They're just a question of who's more likely to win given information about one game. But later in the series, there's kind of hidden assumptions that we have to pay attention to that affect these calculations. Are there any questions about this, by the way? What's going on here?
I'll ask a question.
Yeah.
Then I'll ask it out loud. How did we go from the 1.5 to the 75?
So I believe that these teams are evenly matched. So between these 2 cases, each one of those is equally likely. So we have a 50% chance of being here and a 50% chance of being here. So the total win probability is the average of these 2, which will be 0.75. Are there other things? So I don't know if you've heard this question about birthdays. I don't know how many people are in this room, maybe roughly 20 years ago. So what do you think the chances are that 2 of us standing in this room, or sitting, have the same birthday? 45%?
Maybe I would think it would be.
Yeah.
Yeah, it certainly seems like it could be low. Maybe the intuition that you might have is that for a given person, if you pick a day of the year, what is the probability that that person has a birthday on that day? Pretty low, 1 out of 365. If you don't know anything about the person in advance. And if you go through 45 people, it seems pretty unlikely that those birthdays are going to land on the day that you've chosen. But our question is a little bit broader. I'm not asking for the birthdays to land on a specific day. I'm just asking for 2 of them to match. I don't care what day. So it seems like the chances could be a little bit higher. So in order to think about this problem, I want to try to think about the number of ways that the birthdays can be distributed throughout the year. So how many ways do you think there are? How many different birthday lists do you think that we can have? I'm just going to assume that there's 20 of us in here to make my calculations a little bit better. What's that?
So there'd be 20 days.
But that'd be
Possibly.
different.
Some of them may end up being the same. In fact, that's kind of what I'm hoping
Okay,
for.
max.
Yeah, this is certainly max number of
How many
20,
different
yeah.
combinations of dates could there be?
Well, let's just think about the first person. They have 365 possible birthdays.
Yeah.
So they have 365 choices. So 365.
That's if you're going by the day, were you trying to go by the month only?
Oh, yeah, I'm thinking about dates throughout the year, but not worrying about the year itself. So if you and I are born in different years, but on the same day, I'll count that as the same birthday. But if we're born, if I'm March 14th and you're June 14th, then those are different days. So there's 365 possibilities per person. So if I go through my list of 20 people, how many lists of possibilities are there?
365 to 20,000.
Right. So each person has 365 options, and you go through the whole list, there could be 365 to the 20th different birthdays. So 365 to the 20th possible birthday lists.
That would be correct.
Okay, so now my question is, how many of those many lists will have the property that two of them lie on the same day? I think it's going to be easier for us to think about how many lists do not have that property. That's a common trick in this business, because the number of ways to land two or more birthdays on the same day, I have to go through 2 and 3 and 4 and all these things and check all that stuff. Seems like a lot of work. So I feel like I'm better off just trying to check to see which of these lists have birthdays that are all on different days. So when you ask the first person what their birthday is, you don't care because nobody's been selected yet. So it's not going to match any of their previous birthdays. There aren't any. So they have 365 possibilities, and it doesn't make any difference to us what it is. What about the second person? Right. They cannot, if we get our wish that nobody's birthdays match, they cannot have the birthday on the same day as the first person. So they only have 364 possibilities. The next person? 363. Yeah. And I'm going to keep going like this until my very last stop, which will be the 20th number that I encounter, which I think is 346. We have another way of writing this, by the way. It's 365 factorial over whatever terms I want to cancel away. So 365 factorial contains a huge product, including everything that's less than 346. But I want to get rid of those, so I should divide by 345 factorial. Incidentally, that happens to be 365 minus 20 factorial. So I've got this many total birthday lists, and this many lists with the property that nobody has a birthday on the same day. So what do you think the probability is that at least 2 people have a birthday on the same day? All right. So the number of possibilities that are bad divided by the total number of possibilities. And I should take 1 minus that. Exactly. So 1 minus this number, 365 factorial over 365 minus 20 factorial. All of that over 365 to the 20th. And if you don't have a calculator, you probably are in trouble. But I think it probably is around, it looks like a roughly 1/2 chance, something like this. So much, much higher than anticipated. I remember this exercise being done by my undergrad calculus professor to sort of drum up math excitement. And we had, I think, 50 people in the class. And, he does this thing where he says, I'm gonna make you a bet for $1 that, somebody, two people have the same birthday, and everybody's like jumping on it because they think it's so unlikely, like how could this even happen? But in that case, with 50 students, it was approximately 97% chance. So he was in good shape with his bet. So, all right. Any questions about this?
Just because I was the smart aleck kid in class.
Great.
How do you deal with leap day birthdays?
Oh, yeah.
How do you factor that in?
So,
I think we just use 366 instead.
But how do you?
yeah, so we'll have to take into account the fact that very occasionally somebody has a birthday of
Anybody was born on
366th
leap day
day.
before you start them.
And just know in advance that nobody has a
Very
birthday on
simple
February
process.
29th.
But statistically, that wouldn't make a significant difference for the reason.
It's true that it wouldn't make a significant difference, but it is something I agree.
The more people who were born on leap years, the more it would affect others,
Yeah.
right? Like for
Yeah,
instance,
so
you guys
I
were in
think
class
that
in
we have to take
2006,
into
half of us
account-
were born on a leap year, so we have a higher possibility of being born on.
We then use 365 and a fourth.
If I had to
Thinking
guess,
that roughly
I
1
think,
and 4 would have an additional possibility.
so I think, yeah, one sec. Oh, yeah, go ahead.
How do you simplify this expression to use your calculator? Because my
Oh.
calculator says overflow.
That's it.
Yeah, that doesn't surprise
365
me.
factorial alone is gonna.
Yeah.
Unless you got.
It's a hard question for the calculator. You'd have to have a computer.
At the same time, I wasn't trying to do 365 factorial.
Yeah, but the calculator will attempt to do it, and it will have a problem.
So how do you do that?
I think you maybe have to have a computer to do it, or use smaller numbers, or maybe do it by month or something. Yeah.
So if you're dealing with the year, you can't use a smaller number. I mean, that's your scenario.
Well, one thing that you can make smaller is the number of people in the room.
Well, you
So-
could simplify that factorial there a little bit.
I can, yeah. So this can be 1 minus 365 factorial over 364, or excuse me, 345 factorial, all over 365 to the 20th. But no, I agree, there's no question that the computer's going to have problems. This would be a better problem, I guess, if we had a smaller number like 4 here.
And there's no way
Like
to
this.
just do factorial from 365 to 346 again.
The calculator may not be
Because
able
it'll
to do
probably
that.
try to
Yeah.
move whole.
Regarding the question about the leap year, we assumed that each day of the year is equal probability for being birth. That was kind of an implicit assumption I didn't say. But we can modify it in general if we believe that certain days are more likely than other days. In that case, February 29th would have 1/4 the probability that any other day has. And we'd have to modify our analysis to take that into account. I've looked at some data on this, and it actually, there are certain months that are more popular birthdays by a little bit. Certain months are more popular for, so it's not entirely accurate, this model, but it's probably in line with the type of questions that you'd be seeing.
Christmas September.
I could have modified the question by asking for dates in a month. So assume every month is 30 days, and then your calculator would be able to handle it. So how many people do you think have a birthday on the 23rd of a month or something like this? By the way, we know that if we group 366 people in the room, 2 of them are going to have the same birthday with probability 1. How does our technique account for that? Is it consistent, or do we need some other method, or is this just somehow blow our minds and we don't understand how that works?
That's just the probability of it, though.
Well, this is supposedly a probability using 20 people. You see the 20 here. But if I go through and try to put a 366 in here, it doesn't make sense. So-
just gotta think it's sort of more intuitive like
In fact, even if I put a 365 in here in place of 20, what happens is this denominator is 0 factorial, which is defined to be 1. So this becomes 365 factorial over 365 to the 20, which is a tiny, tiny, tiny number. So 1 minus that is really close to 1. So if I put 365 people in a room, it's probably believable that you think that most of them are going to have, there's going to be 2 birthdays on the same day. It would take an incredible conspiracy to have every day of the year covered by these people.
Be impressed with that.
Yeah. Okay. Any other questions? I mean, I'd like to be able to answer some questions that you're particularly concerned about for the upcoming competition, the things that you're worried you won't be able to discuss with the students that you have. I've seen some other, these are 2 examples that I sort of pulled out, things that I've seen in the past, but know some other examples.
It is the concepts of cross to most of them. When you're dealing with permutation versus combination, you know, get them to sort of take the form of the same.
Right.
And really being able to break down a story problem and to understand, well, what am I dealing with here? Is this a permutation problem, combination problem? How is it? Will it be easier to find the inverse of my probability, or basically to break down the story problem and to figure out what math would I need to use to solve this in the easiest, fastest way.
Right.
I think that's the big thing to try to.
Yeah. I understand.
So it's not a very specific question.
One question that I saw involved suppose you have a 5 by 5 by 5 cube, and it has 5 of 6 faces painted. So I'm imagining taking a cube, which is 5 by 5 by 5 units, whatever units you want. And the cube has 6 faces on it, and we've painted 5 of them. Now I'm also going to assume that the cube is cut into 125 1 by 1 by 1 cubes, all having equal size. So we've got this big cube, it's 5 by 5 by 5, and we slice it up into little pieces. The number of pieces that you're going to get is 5 times 5 plus 5, which is 125. Okay. Then we'll choose one cube randomly. And roll it. So like a die. What's the probability that a painted side comes face up? So what is the probability?
So we randomly picking one of the 125 cubes within the bigger cube to roll?
That's correct.
So there's 25 sides.
Yeah, but the corners you can't count. I mean, you know,
But on the, if it's
But
a
yeah,
5 by
there's
5,
25 on
if it's
each
5 by
side.
5, there's 25 pieces in there that are
On
painted.
6 spaces.
No, there's 25 pieces on that one side that are painted.
So
One by one.
Well, there's 750 faces altogether. Because you gotta look at every face of every little cube, right?
Right, yeah. But we do have to take into account that some cubes won't have any paint on them at all, like the interior and the bottom will be. Some cubes will have 1 face, some will have 2, and some will have 3, right?
Oh.
So how many are going to have no faces painted?
More.
What's that?
Well, no, more than one. You have 2.
One more. All of your interior and the.
Right.
All the interior cubes and most of the one face.
Right, so 27 is close, so you're thinking 3 by 3 by 3, right? That's where that's coming from. I also have to keep in mind that it's only 5 of the 6 faces that are painted. So it's actually,
One's less.
right, so it's 4 by 3 by 3, yeah. Yeah. So there's an extra, I think it's 36 on the interior that are not painted. So the 3 by 3 by 3 cube that you're thinking of originally, plus the 3 by 3 on the bottom, which is another 9.
Right.
So
From
from
go over to
It says
the
five.
next one on either side.
Probably one of
So 36 cubes have none. What about one?
But I mean,
Where
I
are we with
remember
that?
doing this.
The one, the interior 3 by 3 on 5 faces.
Right, so 3 by 3, that's 45 it sounds like, right?
Oh, 45. Not 45.
So the number that will have one face, there's 5 total faces on the big cube painted, and the center of those will each have one face. Those are 3 by 3 squares on each side. So 9 times 5 sides is 45. Okay, now we're on a roll. 2 faces.
The edges, but not
But we're also gonna do 12 of them from our unpainted side, we're gonna have one face painted because they came from
Mhm.
that side, so we need to add 12 more.
To the 2 faces
To
section.
one face. Because if it's on the non-painted side,
Yeah,
if it's on the edge,
You're gonna have 3.
That's
What is asked for?
So there's 12 more than I was thinking of, so there's 57.
57.
Yeah.
Okay, yeah, good call, thank you very much. So I'm gonna cross this out. Carelessness.
on the
Oh,
bottom.
45 from face from the
so the edge of the unpainted side, yeah.
Yeah, the 2 faces should be 24.
So for the 2 faces, we've got 24.
3 times 1, 2, 3, 4 uprights. 5,
Right.
6, 7, 8 are on top.
So 4 uprights and then 3 times 4 around the top, so that's 16 plus 12, right?
No, it should be 3 times 4, which is 12. And 3 times 4, which is 12, it's 24. Because there's none on the
12.
bottom.
You have your upright.
There's,
Am I thinking correctly?
oh, no, but you've got your 4 bottom corners. Yeah, so it's 24.
There's 4 bottom corners, right?
And then you've got your 4 top corners, which will be your 3.
Yeah. Okay, and then the 3 faces. There should be just 4. And if we did it right, this all adds up to 125. Okay. Now, let's just pretend this is right. I think it is. The probability of having chosen a no face is 36 out of 125. The probability of choosing a 2 face is 57 out of 125. So I'm going to start to write that down now. So that's 36 out of 125. And I'm going to leave a space here to write
Is the
something else.
probability that the face is not painted control?
I'm sorry?
The probability that it's painted or that it's not painted?
It's just that it has a face.
Right.
I'm first thinking about the choice of a cube.
Yeah.
Which of
I
these,
was going to
what are the
mention.
probabilities of selecting each
Right.
of these when we choose the cube randomly?
Right.
So, 36 out of 125 for the no face. Then I'm going to get 57 out of 125 for the one face, plus 28 out of 125 for the two face, and then plus 4 out of 125 for the three face. Now, I have to weight these according to how likely each one is to give me a painted side up. So in the case of the no-face cube, how likely is it that when I roll this cube, I get a painted face pointing upward?
0.
0. So I'm going to multiply this number by 0. This one, the one-face cube, 1 out of 6. So I'll multiply this by 1/6. This one, 2 faces, so 2 out of 6. And then finally, 3 out of 6. So this particular problem involved us thinking about this sequence of 2 events. The first was to understand how likely it is to choose a cube with each of the 4 characteristics that we cared about. And the second was to determine the probability of a painted side up for each one. Notice what's going on here. The probability of choosing a no-face cube and getting a painted side up is this times this. When you see and in probability, times. Now, there's 4 possibilities. Each of them were fine for us. So I wanted any of those to occur. Roughly speaking, we're saying this or this or this or this. And when you see that or showing up, plus. That's why the plus appears here. It's actually important that there's no overlap here, that I can't choose, that these are completely disjoint cases. These describe situations. If I choose a no-face cube, then these other 3 things are of no consideration to me at all. So that's how that sort of calculation is done. Any questions about things, about life? Not that I can answer those questions anyway. Okay. I understand that just sort of conceptually thinking about things is sort of what you're worried about for the students. How do we take this language?
It's abstract rated for middle schools.
Yeah, I understand. I certainly understand that. That's hard for my college students to grasp those principles. Yeah.
It is interesting that all that works out to just be 1/6.
Is it right? Is that right?
Yeah.
Okay. So, yeah, maybe what we're actually doing is, what we're really doing is counting the total number of little subfaces here. So here's another way to think about it. After you divided the cube up into little pieces, we've counted, so there's 125 little cubes, each of which has 6 faces. So there's a total of 125 times 6 faces.
Right.
Some of those are painted, some of them are not painted.
How many of those faces are painted?
Right. So there's another way we can think about the same problem.
That might be a faster way to do
Yeah, so, yeah, I guess in this case, definitely will be.
That's the way I was doing it.
it. Yeah.
Okay.
350
So
faces.
there's
And
125
there's 125
times
times
6 total
5 painted faces.
little faces. And then you have to go through and count the number of painted little
It'd be
faces.
25 times 5 painted faces.
Right.
Yeah.
So we get 25.
So 125 over 125 to 6, 1/6.
25 times, yeah, that's right.
Which is a.
That was the way I was doing it, then you guys confused me doing the rest of it, and okay, so my way will work.
Yeah.
Well, that's
a good way to think about it.
Like, but yeah, your approach, that's sort of my initial process where I'm always looking for, is there a more direct approach? Is there a faster way that you can get there? And frequently it's the inverse or just some frame of reference to that.
Right. Yeah. All right. We can do more. I mean, I have more problems we can talk about, or I don't know if you guys have specific things in mind that you're worried about. Yeah.
I don't know whether maybe we need to address just some of the basic problems, like, selecting 3 students out of 5 or 6 students.
Okay.
Because some of us are a little.
How many combinations can you make?
Right. So the question is,
It wasn't, how many combinations?
If you got 15 kids and you want to choose 2, how many combinations can you make?
right.
Or marbles in a bag.
Marbles in a bag.
What's
And
that?
the- and also the difference of how many ways they can be selected as officers in a club, say, president, vice president, secretary.
Mhm.
Because that would be
So-
different than just.
Slightly different thing, yeah.
Yeah.
So let me try to address the first question first. So this is the question of, if you have a list of 6 things, how do you choose, how many different ways are there to choose 2 items from the list? Okay, so this is ways to choose.
And you just, yeah, conceptually explain why does this formula work, instead of saying, you do this, this is the formula, why is that? That's what I
Combinations with Pascal's triangle, and they can do that quicker than remembering the formula.
Right.
If they remember how to.
So let's just imagine, okay, so here's my list of 6 items.
But it's a lot easier.
Lots of dots.
Draw a triangle. Than remembering the formula.
So I'm thinking of ways that I want to pick 2 dots from the list of dots. So first of all, my pair could include the first dot. And how many ways are there of choosing dots that will include the first dot? 5. So I'll write that 5 now. In addition to that, now how many ways are there that will include the second dot that I haven't already seen? 4. So I've already seen second and first dot. So there's 4 more. What about 3? Plus 3 plus 2 plus 1. So, right. So this is what we're thinking about when we're thinking about how to choose things from a list of 5. Now in this case, we didn't care about the order. So, roughly speaking, let me use A, B, C, D, E, and F instead. If I'm choosing 2 things from the list, I could do A, B. But we treated A, B as the same as BA in this example. So if I go through the list of things that include just A, you have A, B, A, C, A, B, A, E, and finally A, F. And then when I get to the next step, which is to try to find the number of ways of writing down a list of things that include B, I'll come across BA, which we're thinking of as being the same as AB. The order doesn't matter. If the order matters, what's going to change?
BA to baby.
We count.
You get the same amount.
Then we go 6 plus 6 plus 6.
So BA, BC, BB,
Or 5,
CE, and BF.
6 elements.
So in this case, these 2 are, I don't think of these as being the same anymore.
So instead of the number reducing, it stays the same for each.
Correct, yeah. So that's the distinction between these 2 cases. At each step, in the first case, we eliminated things based on having seen them already. But in this case, I haven't seen them already. It's a different deal. So in this case, it'll be 5 plus 5 plus 5 plus 5 plus 5. Oh, excuse me, one more 5. So 6 times 5. And one thing that's probably worth noticing is that this is 6 factorial over 4 factorial.
2 elements equals 6.
Right.
And then
Correct. So when I'm picking 2 elements, I'll think of all the ways that I can choose those 2 elements. But I don't want any of this, I want to pick the same element twice. And the number of ways of doing that is 4 factorial. That's good. What if I ask the same question about choosing 4 elements from a list of 6? What's the difference between that question and the one we just asked? So if I say,
6 factorial with 2 factorial.
Maybe, I don't know, I'm not as convinced.
Well, can they be in order or does it matter?
So same question, the order matters.
Okay, order matters.
So, after thinking about it, I mean, so what do you guys think? Is 6, or do we agree with 6 factorial over 2
A lot
factorial?
more, because you can have lots of orders of those 4.
How many ways are there to order the 4 things? So, it seems like whatever I'm getting, I maybe have to multiply by 4 factorial, but what are we multiplying by 4 factorial?
Yeah.
Let's think about it this way. Let's forget about the order for a moment. We'll get back to that. Let's assume that the ordering doesn't matter. So if you're choosing 2 elements from a list of 6, there's got to be just as many ways to exclude 2 elements from a list of 6.
Right.
So the number of ways of choosing 4 has to be the same as the number of ways of choosing 2, assuming that the order doesn't count.
Right.
Because not choosing is the same as choosing from our perspective. So what distinguishes the 4 case when the order does matter?
There's so many different ways of arranging 4 elements and arranging 2 elements.
Right. So, roughly speaking, if the order doesn't matter, so if I pick, the order doesn't matter, then it looks like I want to do 6, choose 2. I'll write out this formula so we can see it. 6 factorial over 6 minus 2 factorial, 2 factorial.
And then doing 6 times 4, you get the same factorials.
So we'll get the same thing when we do 6 choose 4. So we can sort of see the formula working, the formula that we sort of took for granted maybe before, is kind of working in that more conceptual sense. That when you do 6 choose 4, you get 6 factorial over 6 minus 4 factorial over 4 factorial. So these seem to be the same thing when the order doesn't matter. Now, if I've already chosen the 2 elements, how many ways are there to reorder the 2 elements? 2. But if I've chosen the 4 elements, how many ways are there to reorder the 4 elements? Right. So in this case, if the order matters to me, say this vice president, president, secretary question comes up, and so it matters who gets which role. Compute this, and then I would have to multiply it by 2 factorial. Let me write that down. If the order matters, the number of ways would be 6 factorial over 6 minus 2 factorial times 2 factorial times the number of ways that I can reorder the 2 elements, which is 2 factorial. And the other way would be 6 factorial over 6 minus 4 factorial times 4 factorial times 4 factorial. So this extra factor that we're tacking on here, the 2 factorial and the 4 factorial, is counting the number of ways that we can reorder the list that we've already chosen. So this is how I usually think about it. Figure out how many ways are there to select those 3 elements from a list of 7 or whatever it is. And then think about how many ways that we can reorder that list of 3 elements. So let's take your example about the president, the vice president, and the secretary. So assume we have a class. 7 students who must choose. Three things: president, you know, the boss, the vice president, and I like your secretary, so I'm gonna go with that. How many different possibilities are there for the three positions?
Three positions. 7, 6, 7, 10.
So, first of all, we should try to count the number of ways to choose 3 people from a class of 7. So what is that? 7 times 6 times 5.
You're saying just pick 3 people?
Yeah.
Combination,
Correct.
Do the combination, so it's 35.
Okay. So where we're getting that though is
combination 7
7 factorial over 4 factorial times 3 factorial. That's where you're getting that. And that comes out to be 35. So these are the ways that you
Yeah, I
do
think
it.
Pascal's
But in this case, it wouldn't matter.
right.
In this case, it wouldn't matter.
Yeah.
Correct.
35.
So what has to change about our answer to get the correct answer?
How many different ways can you arrange those 3?
Correct. Right. And how many is that? 3 factorial. Yeah, exactly. So the correct answer will be 35 times 3 factorial, which is 35 times 6.
Which is kind of taking a long way around. So,
Yeah.
because we could just do 7 times 6 times 5,
Okay.
right? Because that
Yes.
has
So
7
what's-
possibilities for the president
Right.
times 6 for the
Right.
vice president times 5 for the secretary.
What you're noticing is
But this is building in conceptual understanding of both.
right.
Yeah.
No, you're right. If I don't care about the combination at all, if I don't care about just picking 3 people at random and just here's my 3 people, then yeah.
And
But-
using Pascal's triangle is, you find an easier way. How does it go that?
All combinations.
Okay.
And
I've never
So
used
it-
Pascal's triangle.
like if you take 1, 2, 1, that would be, what, 2 choose 0, 2 choose 1, 2 choose 2. So there's one way,
Oh, it's a scheme.
yeah,
That's what it is.
it's very simple. You just always have to remember that your first element in the row is choosing nothing at all. And then the last element in the row would be choosing all.
Okay. You just extend it to.
You just keep going and go right.
By the way, yeah.
So if you're only talking about 1 7
So I guess if you're going to memorize Pascal's triangle, that does give you a list of these combinations. But what those are coming from are the list of these calculations. And if we can do the calculations, we're better off, I think, than memorizing a list of numbers, maybe. I don't know.
I don't look at
All right. Are there any other questions about this that people want to talk about?
Actually, she was.
I feel like frequently probability gets focused on more than odds, and not many people appreciate the distinction between the two. If you're asking what the odds of this happening versus what the probability of this happening.
Okay, well, what is the distinction?
The odds are the number of successes versus the number of failures.
Right.
And probability is the number of successes over the total number of possibilities.
Right. So when
And
you
it's
say something has 2 to 1 odds, you're saying
Right.
it's probability 2/3 of it happening. Yeah.
Right. I think that's something that gets kind of overlooked frequently.
So
It's
you
one
have
of it's
your
one of those like
Vegas
little
betting on
nitpicky
sports,
things in a
which you
question
should
that could easily.
What's that?
It's one of those like things in a question that could be overlooked if you recognize the probability question, but there's
Okay.
the odds it's actually asking for a different thing.
Yeah.
I don't know that there's much to talk about there other than I notice that's one thing that sometimes the kids don't make a distinction between. And And a lot of people use the words interchangeably.
I'm sort of guilty of that too, I think. But I certainly understand when you go to Vegas, if you're betting on sports,
Right.
you know, they
Well,
tell
in-
you,
In the
you
context
know,
of the questions, if you're being asked, you know, what are the odds of this, what's the probability of that? At a glance, it looks like it's sort of the same question, right? Because most people use interchangeably. I don't know, just, you know, read a question.
yeah, I understand that's definitely something to watch out for. So what you're saying is, if you have, if something has 2-to-1 odds, I think this is the notation that's typically used for that. What this means is, these are odds, the probability is 1 over the sum of those numbers.
2. Using 2 to
In
1.
favor of.
2 to 1, if that's odds in favor. Then there's odds in favor, odds
It'd be
against. Two would be the
two-thirds
success.
in favor, 1/3 not in favor.
We don't get odds.
That's not the way I
Yeah,
understand
very
it.
rarely do we get
I
odds.
wasn't sure if it was ever.
But you do see them in academic books sometimes.
Right, so you'll have to-
What your probability is.
Oh, okay, all right.
Actually, I think there was an odds question one year because,
Was?
that was, yes, there was,
Really?
because,
I don't
yes,
remember.
one of my kids,
Right, it
I like,
it's very rare.
yeah, but it does show
Oh, it
up.
does
And there's
show-
a
it
big
does
difference
show
between
up.
odds and probability.
Yeah, that's
Yeah.
just the point that, but,
Yeah.
the first
The way
time
that
I
I
read
see
the
it,
numerator.
I just looked at the odds for next year's World Series as you.
Uh,
I saw this as the first one, 5-to-1 for the Dodgers. But I think that means probability 1/6. I think is how
So
they
that'd be the
report
odds
it.
against.
Yeah, so that's how they're reporting it. So maybe it has to be, maybe it's different in
So,
different
well,
contexts.
so
This-
there's
this
odds in
is how I
favor
see
and
it.
odds against, and, yeah. So that'd be the probability of not,
Right,
but then it's flipped, yeah, odds in favor, odds against flips, so it's right.
right.
But it doesn't come
So yeah, I think this means 1/6 probably. In this
if
case,
it's
probability
not
to
what we
win,
asked. Yeah.
but 5-6 to not win the World Series. And I don't know, that seems a little high for the Dodgers.
Depends on campus then.
Yeah. Okay. By the way, Pascal's triangle, you know where those coefficients are coming from
Or the
originally,
expansion
right?
of x plus 1 is the n.
Yeah, so if you take this expression a plus b to the n, and you expand it all out, and you read the coefficients off, you get one of the rows of Pascal's triangle. And the row that you get depends on the choice of n.
There are problems like that that come up actually in Mathcounts. What's the coefficient in the expansion of this, of this polynomial?
If I write out this expression, you see that we have n things. This is times, sorry about that. If you're looking to see what the coefficients are here, if you think about how this expansion works, the terms after doing all of this massive FOILing will have a times a in every slot.
Right.
And then in the next term, there'll be an a in every slot except 1. So what you're counting is the number of ways of choosing b one time from the list. So that's like saying n choose 1. And then you go to the next term, and then there'll be 2 b's, the rest a's. And then you're looking at n choose 2, and then n choose 3, and it keeps going. And it has this symmetry because n choose 1 is the same as n choose n minus 1. There's the same number of ways of choosing 1b as there are of choosing 1a. So, when you look at Pascal's triangle, what you're really looking at are the coefficients from the binomial theorem, the expansion of this expression.
Is the conceptual time actually that
So that's usually how I'm thinking about Pascal's triangle. I'm just thinking, okay, this is the binomial theorem, and these lists of numbers are telling me the binomial theorem.
Wonderful. Thank you so much. We appreciate you coming, Dr. Siegel.
Oh, you're very welcome.
Thank you so much. Was that helpful?
Yes.
Yes? Great. Well, we will be trying to do something like that at each of our coaches' workshops from now on. So, any questions before we let you guys go? The evaluation sheet, please fill that out and you can leave it with me or with Judy. And I think that's it. We will see you guys in February. And let us know if you have any questions. All right. Dr. Timmons, would you like a shirt? I'm not sure what size you are there.
Thank you.
Thank you.
Pleasure. I'm really hoping it's useful. I know this is not my sort of this is not my area, so I'm just trying to.
Well, it's just giving the teachers
Now it's working, just watch.
Questions or anything?
So I get there.
Great.
And you're welcome to
February 1st. Actually, it would be a good thing to do, actually. What sort of, just a coaching's kind of.
Well, we have coaches and advisors. For judges that are in the judging
So they're trying to reschedule it instead of get refunds, but.
For those who have not received the Mathcounts t-shirt, I did bring some today. You may have one. Some other giveaways. And they'll be worth something someday. We've changed the logo. You know, these are old stuff.
Already.
Antiques.
I didn't ask you about Emily and Jesse, how that all ended up.
Yeah, actually, that'd be great. So thanks for inviting me.
Jesse,
Thank you, we really appreciate it.
Emily did not come out.
Yes, there are all sizes over there.
Phyllis Scott. Yeah. Phyllis got very involved.
There you go. And they are pretty small. But now anyway.